What if the biggest mystery in all of physics isn't a thing at all? For decades, we've been told our universe is basically haunted by these invisible forces. We call them dark matter and dark energy. Well, today we're diving into a really radical idea. It's called the CRET Cosmological Model, and it suggests these might just be cosmic ghosts. So let's see if we can bust them. Think about it. The standard story of our universe has this massive hole in it. We're told we only understand about 5% of everything out there, and the other 95% is made of, well, mysterious, invisible stuff. But what if that's just a ghost story we've been telling ourselves? What if the universe isn't missing a single thing, and we've just been reading the map wrong this whole time? And then there's this number. It is, and I'm not exaggerating, one of the single biggest embarrassments in modern physics. That's a 1 with 120 zeros after it. And it represents the gigantic, gaping chasm between what our best theories predict about the energy of empty space and what we actually see. I mean, this isn't a small mistake. It is a universe-sized failure that screams at us that our current model is profoundly broken somewhere. Okay, so here's our game plan for today. First, we're going to lay out the problems, the big cracks in our current understanding of the cosmos. Then, we'll introduce the new contender, CRET, and its pretty wild idea of an elastic spacetime. We'll see how it tries to tackle all those old puzzles, put it in a head-to-head showdown with the standard model, and finally, we'll talk about how we could actually prove it right, or, prove it wrong. All right, let's get into it. Section 1, Cosmology's biggest puzzles. So our standard model of cosmology is called lambda CDM. And look, it's been incredibly successful at describing so much of what we see out there. But it's kind of held together by some pretty shaky assumptions. Yeah, to make all the math work, our best theory of the cosmos has to just add these huge, completely unknown pieces. We need something called dark matter to act as this invisible cosmic glue to keep entire galaxies from flying apart. We need something called dark energy, a mysterious force that's somehow stepping on the gas and accelerating the expansion of the universe. We have that absurd 10 to the 20 problem we just talked about. And on top of it all, we still can't connect our theory of the very big, that's general relativity, with our theory of the very small, quantum mechanics. It's like having this beautiful car that only runs on imaginary fuel. So that brings us to section 2, a new idea, CRET. If the old model is having so many problems, what's the alternative? Well, this is where CRET comes in. It stands for Constraint-Resonance Emergence Theory, which is a mouthful, I know, but all you really need to remember is that this isn't just a patch on the old model, it's a complete reimagining of what space-time itself even is. So here's the absolute core idea. CRT says that space-time isn't some passive, empty stage where the show of the universe happens. No, space-time is the show. It's an active, dynamic fabric that's literally woven from quantum entanglement. That bizarre, spooky connection between particles. So think of it less like a blank canvas and more like a vast, shimmering spider's web. A tiny twitch in one corner can be felt all the way across the entire structure. And this one single idea changes literally everything. In this view, gravity isn't even a fundamental force anymore. It's something that just emerges from all the connections in this network, like a pattern appearing in the web. This web also has this really clever built-in way of just canceling out all that extra vacuum energy, so that 10 to the 120 problem, it just goes away. And most importantly for us, this fabric of space-time has an elastic response. It can stretch, it can pull, it can react to the matter and energy inside it, kind of like how a trampoline bends when you stand on it. Now for section 3. Spacetime's elastic response. Okay, this is where it gets really, really cool. Let's see how this one concept, this idea of an elastic reality, proposes to solve cosmology's biggest mysteries without inventing any new dark stuff. Okay, first up, galaxy rotation. The standard view says galaxies are spinning so fast they should have ripped themselves apart by now. So we had to invent this giant, invisible halo of dark matter to provide the extra gravity to hold them together. The CRT view? There is no extra matter. Instead, a huge, massive galaxy creates tension in the fabric of space-time all around it. It's an elastic back reaction. And that tension provides the extra gravitational pull needed to keep the galaxy in one piece. It's a property of space itself, not some ghost particle. So what about the universe's accelerating expansion? Well, the standard model invents dark energy, this mysterious anti-gravity force that's pushing everything apart. CRET suggests something a lot more natural, that the fabric of spacetime, after the initial chaos of the Big Bang, has been in this state of high tension and is now just slowly relaxing over billions and billions of years. This slow relaxation creates a gentle outward push that we see as acceleration. It's not a new energy, it's just the geometry of the universe finally settling down. And what about that gigantic 10 to the 120 problem? While CRET tackles it head-on with this really clever trick called sequestering. Imagine the energy of empty space is like a constant deafening hum in the background. The CRET model basically proposes that the universe has a built-in noise-canceling feature that just tunes out that background hum completely. The problem doesn't even need to be solved, it's simply designed out of the system from the very beginning.
Okay, that brings us to Section 4, a side-by-side showdown. It is time for a direct comparison. In this corner, the reigning champion, the Standard Model, Lambda CDM. And in this corner, the challenger, CRET Cosmos. Let's see how they stack up. So, when you put them right next to each other, how do these two completely different ways of looking at the universe really compare?
You can see the difference in philosophy here is just stark. Where the Standard Model keeps adding new mysterious ingredients, new particles, new energies, CRET changes the recipe of reality itself, using the properties of space-time to do the work. That 10 to the 120 problem is this massive unresolved paradox for one model, and it simply doesn't exist in the other. CRET even claims it might unify gravity and quantum mechanics. Ultimately, it's a bid for a more elegant, more economical universe, one that explains all the same things we see, but with far fewer weird assumptions. But look, elegance isn't enough in science. A beautiful theory has to make predictions that we can actually go out and test. So for our final section, number 5, putting CRET to the test. How could physicists figure out if this is really right or if it's just another beautiful idea that doesn't pan out? And this is the great part. It's not just philosophical. CRET makes concrete, testable predictions. Scientists could run lab tests to see if empty space itself creates gravity. CRET says it won't. They can use our new telescopes to look at very, very distant galaxies to see if their rotation actually changes over cosmic time in a specific, predictable way. And, maybe most excitingly, they can re-examine famous images like the bullet cluster. CRET predicts that the gravitational lensing, the way light bends around it, should follow the visible matter perfectly with no offset ghost of dark matter. A direct hit there would be a huge blow to the classic idea. So, in the end, we're left with this choice. Is our universe filled with invisible ghosts that make up 95% of everything there is? Or is the very fabric of reality an active, elastic, shimmering web, something far more surprising and dynamic than we ever imagined? CRET offers a bold answer. Now, it's up to the evidence to decide.